So I've got y equals tangent of x on the board. Like all trig functions, it is not invertible. I've just drawn 2 periods of tangent here, but even with just 2 periods, it's repeating all of its y values. Okay, so to create an invertible function, we need to restrict the domain. So I'm going to be taking a look at y equals, let me draw my axes first. I'll draw the picture up here. I'll write it down here. I'm looking at y equals tangent of x, but I'm going to restrict x to be in an interval that corresponds to 2 quadrants worth of angles. 1 quadrant where it's positive and 1 where it's negative. So I've got my graph of tangent to work with, and I'm also going to be thinking in terms of the quadrants. And I know the rules. I always have to choose quadrant 1, and that's really just strategic laziness. Quadrant 1 is the easiest to work with. Everything's positive there, and the version of quadrant 1 between 0 and pi over 2 is my acute angles where I can use right triangle trigonometry. Excellent. Now, we never choose quadrant 3 because we always want an adjacent quadrant so that we can get a nice connected piece of graph if possible. Okay. So it's got to be either 2 or 4, and usually that's been determined by which quadrant the trig function was negative in. Now, tangent's kind of interesting because tangent is negative in quadrant 2, but it's also negative in quadrant 4. So either of these would give me a quadrant where tangent takes on its negative values. But one of them is a better choice because I can see if I chose quadrant 2 going from 0 to pi, I'd have this asymptote smack dab in the middle of that interval. Whereas if I choose quadrant 4 going from negative pi over 2 then to pi over 2, I get a nice connected piece of graph. So we're going to choose quadrant 4 from negative pi over 2 to pi over 2. So this now is the graph of y equals tangent of x, where x is in the interval from negative pi over 2 to pi over 2. Now that's almost the same as the interval that we used for when we restricted the domain for sine. It's not quite the same because you'll notice I didn't include the endpoints. These are parentheses, not brackets. I can't include them because tangent isn't defined at negative pi over 2 and pi over 2. So I can't add things to the domain when I'm restricting the domain. So for sine, I do include the endpoints because sine is defined at those points. For tangent, I don't. And so then I can say y equals arctan of x, or equivalently y equals tan inverse of x, means x equals tangent of y, and y would be in the interval from negative pi over 2 to positive pi over 2. Okay, excellent. So let's see if we can't evaluate that at a couple of places. So let's try to evaluate arctangent of negative 1 and arctangent of root 3. I'm going to suggest that you pause the video, try to work those two out, and then tune back in and we'll work through them together. Welcome back. Okay, arctan of negative 1. I'm going to call that theta. Okay, and then I know that what this means is that tangent of theta is negative 1 and theta is between negative pi over 2 and positive pi over 2. So I know that corresponds to either quadrant 1 or 4. I look at the fact that tangent is negative and I say, we're in quadrant 4. So my theta is going to be an angle in quadrant 4, but be careful. I don't get there by rotating around this way so that I have a big positive angle. I rotate clockwise so that I have a small negative angle. Okay. So that's going to just be the opposite of whatever my reference angle is. The reference angle is this positive acute angle. Theta is that negative acute angle. Okay. And what I know about alpha is that tangent of alpha is the absolute value of -1, which is just 1. Okay. So I'm always checking, if I'm trying to do this without a calculator, I'm checking to see if it's one of my nice special angles, if it's either a quadrantal angle or if it's pi over 6, pi over 4, or pi over 3. Okay. Seeing a tangent of 1, I'm going to draw my 45, 45, 90. But let's say I wasn't sure. I'm going to draw both of them. I'll draw the 30, 60, 90 too. Okay. So this is a horrible picture of a 45, 45, 90. Okay, 1, 1, root 2, 1, 2, root 3. Okay. So if I take a look, looks like the 45 is going to do it because tangent would be 1 over 1. When I have an isosceles triangle, the opposite and the adjacent sides are the same. So alpha is pi over 4, and we said theta was just the opposite of that. So this angle is going to be negative pi over 4. Excellent. Okay, so let's now take a look at arctangent of root 3. Same basic process. I'm going to give that a name that reminds me that it's an angle. I'm going to call it theta. And then I'm going to say this means that tangent of theta is root 3 and theta is in the interval from negative pi over 2 to pi over 2. But I know that that corresponds to quadrants 1 or 4. If tangent is positive, we're in quadrant 1. So that's super nice. We're just talking about an acute angle. Now we want the angle whose tangent is root 3. Well, if I think about my 30, 60, 90, or if I think about the points that correspond to those angles on the unit circle, I know a root 3 shows up. So I actually don't have memorized what acute angle has a tangent of root 3. I know it's either 30 degrees or 60 degrees. I can never remember which one without drawing the picture. Okay, but now I can see that opposite over adjacent would give me root 3 if my angle is 60 degrees, but that would be in radians pi over 3. And since we're just looking for that acute angle, this is going to be, whoops, pi over 3. So we're able to evaluate it. All right, in the next video, we haven't talked yet about graphing these inverse functions. In the next video, we're going to take a look at what does the graph of arctan look like.